Right. Welcome, guys, to ENG 297, which is your circuit systems 2. This is experiment number 2, which is the analysis of RL and RLC circuits. With you here, my name is Remember Samu. Some of you know me, or some don't already. Unfortunately, we couldn't upload your lab 1, like pre-experiment lab 1. So I'm going to try and upload this experiment 2, of which experiment 1 was just an analysis of an RC circuit, and experiment 2 is an analysis of RL and RLC circuits, right? Resistor inductance and resistor inductance capacitance circuits in AC systems. Right, so what we have here first is the aim of this lab is to measure and display voltages in a sinusoidally excited RL and RLC circuits. Then we need to understand how the impedance of an inductor changes the frequency variations, right, in a circuit. So we go to the apparatus that are needed for this lab. The apparatus that we need a functioning generator. This is the functioning generator. What it does is that it just like mimics an AC signal from a generation station. So we can input amplitude, we can input frequency, period, all those things into this functioning generator. Then we define our own signal. We can change the type of signal we want depending on what we want. We've got about 3 options, which is the sinusoidal signal, the ramp basically is like a triangular wave, but it only becomes a purely triangular wave if you change the symmetry to 50%. Then we've got the square wave. Those are the 3 types of signals that we can actually give using this function generator. And we just take our output from this output node, and we can change the frequency or the range of the frequency from millihertz to megahertz using this knob right here. Right, I'll show you in a second how we can actually do this. But what happens on this type of this particular type of function generator is we can only display certain frequency. We can only see frequency from here, but we cannot see the amplitude that we're giving in. We need to give an amplitude when we're defining a signal, of course. So we need to give an amplitude. We cannot see it here. We can only see it from the oscilloscope. So that being the other type of apparatus that we need for this experiment is the oscilloscope. So the oscilloscope, I shall just switch it on quickly. Let me just switch on the function generator quickly as well. So like what I said, the function generator just displays, this display you see as the frequency. So you can turn this knob, right? It gives you different ranges of frequencies. So the oscilloscope, it's more like a graph paper, right? It just displays, right? In its original setting, the oscilloscope displays voltages. It displays the voltage signals, basically. It doesn't display current, but there's a way, from those who were in the first lab, there's a way of actually displaying current on the oscilloscope, but it's just designed originally to display voltages. It can display input voltage, output voltage, depending on whatever voltage you're measuring across different components in a second. So it displays voltage, and it has 2 axes, like like a graph paper. It's got the y-axis and the x-axis. So the y-axis, basically the amplitude axis, it displays the voltage, the amplitude of the voltage. Then the x-axis, it's the time axis. It displays the frequency, period, all those signal characteristics that are related to the time with the frequency and period. You can display it in the x-axis. So each and every, since they are boxes, each and every boxes, they are represented with a certain what we call channel division. If they write, like in this one, they wrote channel 15V. It means each box, right, in the y-axis, each box in small square, it represents 5 volts, right? So if your signal is covering 4 of those boxes, it means it is 20 volts peak to peak, in other words. Then in the time division, like it say time here, it's 2.5 milliseconds. It means 1 box in this one without any input voltage or any input signal being put. It means 1 box right now is being represented by 2.5 milliseconds. So this is the oscilloscope. It just displays, right? We can play around with the oscilloscope to measure different things once there's a signal coming in, which we shall see during the course of this experiment. And the third component that we needed was a Protec DMM meaning digital multimeter. So this is the Protec digital multimeter that we'll be using in this experiment. So in this particular digital multimeter, as you can see, I've got these two probes, right? I've got these two probes with me. Okay, so these two probes are just basically what we call DMM probes, digital multimeter probes. So there's the black one. Okay, the colors, okay, we try to say black should go to the ground and red should be the positive one, but it does not really matter if you change these. It does not change anything in this particular apparatus, but just try to keep that in mind, right? Like black, we usually put it on the ground, and red, we put it either we want to measure current or voltage. So it's a digital multimeter, right? It measures RMS values. It measures current and voltage RMS values, but not only that, it can measure inductance, it can measure capacitance, it can measure if a diode is working or not. You see, when we start using diodes, it can measure different sort of, it can measure frequency, it can measure many operations. So, but what we do is we always keep the ground on the COM. There's COM, there's micro A dot V, this is voltage. Then there's milli A, this side is for current with milli A and 20A. This is for current side, this is the voltage side. So if you want to measure current, normally we work with milliamps in here or even microamps. So for us not to confuse the scale, what we normally do is we work in milliamps. So if you want to measure current, you just put it in milliamps, and what you do next is that you just turn this knob, right, clockwise or anti-clockwise. You just put it on 20 ohms on milliamps. Once it's on milliamps, it can now measure current. So only if you're measuring current, you put this one either on milliamps or on 20 amps. But you see, now it's beeping because I put it on 20 amps, but this knob is on milliamps. So for it to measure under 20 amps instruction, you just move this here, then it switches off, right? So this is for measuring current. But when you're measuring voltage and anything else other than voltage, right? Anything else other than current, voltage and anything else other than current, you have to put it on the voltage side. This means if you want to measure the temperature, if you want to measure the capacitance or the inductance, if you want to measure the diode, whether that is operating, it's all not broken or not, whether you want to measure the resistance, you want to measure the voltage in decibels, you want to measure the voltage, you want to measure voltage, frequency, and whatever. Everything else that you need to measure, you need to put this probe on the voltage side. This is very important. You need to put this probe on the voltage side. This is on this Protec 506 digital multimeter, which is one of the apparatus that we need to use. And now on the lab manual, it says more apparatus that we need are the 1 kilo ohm resistor, 100 ohm resistor, 0.1 microfarad capacitor, and it was written 10 millihenry. Unfortunately, I could not find this in the lab, so we're going to use 1 millihenry inductor, right? So the first thing that we do, of course, okay, I didn't introduce this machine. We are not using it right now. I just used it as a stand right now for us to put our function generator for you to actually be able to see it. But this equipment down here is just DC supply source. It can supply voltages all the way, I think, to 24 volts, if I'm not mistaken. So it's just a DC supply we're not using for this experiment. But in case you're wondering what's this is just a DC supply voltage. So I just used it so we can have a raised stand for our function generator. Right, so the first thing that we do, once we get our components, the first thing that we do is we try and measure the sizes of the resistors and capacitors that we have, right? We can measure inductances, but depending on the significant figures that are given on this machine, sometimes it might be difficult to measure the inductance, right? But we can measure the resistances and the capacitances to make sure, because we have boxes that are set that we can put our 5 ohm resistors, 10 ohm up to whatever size of resistor that we have, but they might be mixed, right? So we need to actually measure the resistors. So as we know, we actually use those 3 color band resistors in here that have 3 bands, and the 4th band representing the resistivity of the resistor, right? So here what we need is a 1k ohm resistor, or a 1k ohm resistor. If I was to just know it offhand, 1k ohm resistor is represented by colors black, right, brown, black, and red. those three colors, brown, black, red, in that sequence, that represents a 1K resistor. Then brown, black, brown, that stands for 100 ohm resistor. So as I can see in those colors, what I said was brown, black, second band, and red. These three colors represent the size of the resistor being 1K, and the fourth color at the other end, which is gold in this case, it represents the resistivity. That means the deviation from the actual result. So resistivity of this, if it's 5%, it means this resistor can measure maybe from 1005 ohms to 1050 ohms to 950 ohms, something like that. So that's what resistivity stands for. So this one should be our 1K resistor, but I'll measure it just to confirm. And this one should be our 100 ohm resistor, but I'll measure just to confirm. And our 1 millihenry inductor is just something like this that we're going to use. And our 0.1 microfarad capacitor is something like that. We'll measure it again just to confirm. So now, like what I said, we put this one on the voltage measuring side. Once we put it on the voltage measuring side, we set this knob. We want to measure resistance first. We just set it till it comes here where it measures resistances. Now we want to measure these resistances if they are correct, right? So okay, fine, it's refusing to stand. What I'll do, like what I know, a resistor is just a passive circuit element, so it does not matter where I put the positive side or the negative side of this these probes. Then I want to see how much resistance will I measure, right? If I put this across this probe, I want to see how much resistance. As I said, this should be a 1K resistor, right? As we can see, it's 986 ohms, right? 0.986 kilo. So it means this is a 1K resistor. That's correct. So I put it down. Then now, nextly, I measured the one I'm suspecting to be 100 ohm. I just put it here and here, right? Then there we go. Here and here, it's measuring 100 and 100.4, okay? Let me just raise it up. This one, measuring 100.4 ohms, yeah? So that means it's a 100 ohm resistor. Now, that's fine. Now, I want us to measure the value of the capacitance, right? Like what I said, what we do is we leave this one on the voltage measuring side, then we just take the capacitor, but we have to change, right? We have to turn this knob to the capacitance side. Yep, up to there. Then let's see if we can display our capacitance, right? So it's supposed to be 0.1 microfarad. Let's see that. There we go. 1 minute. Yeah, there we go. Yeah, 0.1 microfarad, 0.10 microfarad. So we're using the correct capacitor, right? Like what I said, if you want to measure the inductance, you just do the same thing. What you do is you just press, there's a button written function here. So you just press this button function, then it changes, it shows this inductor, then it's already in henries, then you can measure the value of the inductance. Yeah, you can do that anytime, right? Good. So now, we proceed with the experiment. Now we haven't finished checking. We're finished checking our component, the size of the resistors and everything, but we haven't finished checking. What we should check, because they are probed. Okay, these cables with me right here, these cables that I just put right there, they are called probes, right? So they have different names of probes. These two cables, right? These two cables, with this side being the positive of the cable, and this side being the negative, which is ground. This is positive, this is negative of ground. These cables, and they have the other end, which looks like this, right? These cables, they are called oscilloscope probes. They are supposed to be on this. So we have two channel outputs of an oscilloscope. So we can put this cable on channel 1, then another cable exactly like that one, we put it on channel 2. These channels, okay, as there are two, we can display, meaning two signals at once on the oscilloscope. We can display the input signal and the output signal from the oscilloscope. Then, now we have another cable because we need to take the output from the function generator, right? We need to take the output. So we use this cable, right? We use this cable. So this cable normally we call it a BNC probe, right? We call it a BNC probe. It's just, well, if you see, it just has two outputs as well, right? Ground and positive. It can work if you put it on the oscilloscope as well. It can work, right? So, but it's actually meant to be from the function generator. It's a BNC probe, so we put it on the output of the function generator, like this, right? But before I put it here, what we need to check is if these cables are working, right? We need to check if these cables are working, because sometimes the cables won't be working. The cables will be broken, and if you work with a cable that's not working, it means at the end of the experiment our signal will not come out correctly, and we will face problems maybe 1 hour, 2 hours trying to fix the circuit diagram on itself, but maybe it's not the circuit, right? It's actually the cables. So we need to check. So checking these cables, what they should do, we use an oscilloscope to check them. What they should do is they should give us a square wave if they are working. But there's a connection this side of the oscilloscope. If you can see, there's this knob of the oscilloscope this side. The top one, it's the positive side. Then you connect a ground one to a ground, right? This is channel 1 that I'm testing. So let me just remove this so that you don't get confused. I'm testing channel 1. So what I do is I press auto set. Auto set is like if you're, let's say you're running a simulation. Auto set, it works more like a run, you know, that run button that you press for your whatever simulation to run. That's like auto set. So you just press auto set. Then if you get a square wave, it means exactly, see, you get a square wave, it means this cable is working. So we just remove it and we put it aside. One very good cable. What do? We put another cable. You can use any channel to test, right? You have to use channel 1 only. You can use any channel, but I just want that to test one by one so that there's no noise on the oscilloscope. So take this one and connect ground to ground and do the same, auto set. You see, the cable is working. If you want us to use channel 2 to test if the cable is working, if we get the same result, we just auto set again. Exactly. So it means the channels are fine, right? And the cables are fine. So these two oscilloscope cables are working, but we need to check also the BNC probe, which is because this is the probe that will transfer our signal from the function generator, right? So we need to check if it's working. If it's not working, then we will suffer, right? If it's not working, then we are going to suffer. So let's check it out. Connect it to any channel, just like those cables. Connect positive to positive and ground to ground. And we auto set. Exactly. We get a square wave. So it means all our cables are working for now, right? That's perfect. That's very good. So we now put this one, it belongs here, right? Then these are channel cables. This belongs here and this here. Channel 1 and channel 2 output, right? Then the third thing that we're going to use, basically, of course, we don't connect those sort of resistors, inductors in the air, right? We connect them on the breadboard. Now, just a few things about the breadboard. These 4 connections, 1, 2, 3, 4, right? They are not connected to this automatically, right? If you want to use them, you have to actually get jumpers from here to the breadboard, right? Otherwise, the way it is right now, they are not connected here. That's the first thing. And as you can see, breadboard's got some brilliant colors, right? Blue, red, white, that's what I can see. So there are these 2 sort of columns, I can call them columns, depending on how I'm holding it, or rows if I'm holding it like this. There are these 2 rows, right, that are in between the red and the blue line. These rows are labeled plus and minus. These rows are connected. If I'm holding it like this, they are connected horizontally like this, right? They are connected horizontally like this. It means if I give 5 volts at this terminal, this whole row, it's 5 volts, maybe sometimes up to the middle. You know, this section here, sometimes there's no connection between this side and this side. But the assumption is normally is if you put 5 volts here, this whole row is 5 volts. If you put 0 volts here, this whole row is 0 volts. So it means just in between these 2 lines, the black and blue line, our rows are connected horizontally like this. Now, if we go into the mid section of the breadboard, right? This mid section has got 1, 2, 3, A, B, C, D, up to E. So it goes 5 sort of points. These 5 points, if I'm holding like this, they are connected vertically. It means if I just put any value here of a voltage, it means that whole sort of line A to E, it's actually now a node, right? That has exactly the same voltage. So it's connected sort of horizontally. If I look, vertically, if I look at the midsection of the breadboard. So, and the other end is to have, again, those blue lines and red lines. So this becomes like a one whole breadboard, if I may say, right? So these are just about 2, 3 breadboards that are attached to one sort of base, right? To just have more space to work on. So this is just the breadboard. We're gonna use it to connect our apparatus. Then of course we will use jumpers. We can call them jumpers, can call them cables, you know, they're just wires, if I may say, that have minimum resistance, like sort of negligible resistance compared to the resistance of the circuit itself, right? Now, what do we need? That was the part or the section of the apparatus or the whatever we needed to proceed with our experiment. Now, we continue with the experiment. It's saying, first thing, set the function generator to 10 kilohertz sinusoidal wave. So it gave us the frequency, it gave us the type of signal, sinusoidal signal. Now, and adjust the amplitude to 10 volts, right? It means amplitude is 10 volts. Now, if you're talking about signals, right? If you're talking about signals, right? Normally a signal is a sinusoidal signal. It will have something like this, right? So if they say amplitude, right? Amplitude, they're talking about this, right? To be 10 volts from zero line, this is zero line, to this. That's saying it's 10 volts. So as our input signal, what we should give is 20 volts peak to peak, right? Peak to peak. So it means from this peak down to the negative peak, because here we'll have minus 10, right? This value will be minus 10. So from peak to peak, it will be 20 volts, right? That's what it's saying. Amplitude 10 volts, so peak to peak 20 volts. Now, use the oscilloscope to confirm both the frequency and the amplitude of this. So what we're gonna do is the first thing, right? Before we check out the output, right? We haven't connected anything yet. We want to try and put this frequency of 10 kilohertz here, right? On the signal generator. Let's go. So that's 2, now I'm at 7. I'm gonna go 9, 10, 1. Okay, it's quite sensitive. There we go. There we go. 10.03. So I've put 10.03. I hope that's clear. Yes, that looks clear. That looks clear. Yeah, 10.02, 10.03. You can see that. Should be, yeah, that should be right. Now, I've set that frequency, right? Then the next thing that I'll do is to try and give, like what I said, these are 3 signals, right? Sinusoidal, triangular, square. I'll press this one. It means now a sinusoidal signal is coming out, right? But I don't know what amplitude is this signal yet. I need to verify with the oscilloscope. So what I'll do is I'll connect the positive of the oscilloscope, with positive output of the signal generator, then the ground of the oscilloscope probe with the ground of the BNC cable. Then I just put it like that. Like what I said, you run auto set, right? You run auto set. Once that happens, you run auto set. There we go. So we have this. Okay, just this cable not close your view. So we have that output signal, a sinusoidal signal coming in from there. So let's check. So the sinusoidal signal, it gives us the frequency written on the oscilloscope. It's showing us 10.03 kilohertz, right? 10.03 kilohertz. Maybe you cannot see this. Let me just try and, there we go, right? It's showing us 10.03 kilohertz, right? 10.03 kilohertz. But the peak-to-peak voltage at this instant is only 2.16 volts. And we need this to be 20 volts peak-to-peak. So we adjust the voltage knob from our signal generator, from here, right? So let's adjust and we'll be checking the value there. We're at that. We haven't gone there, we haven't gone there. Let's just auto set. Where are we now? 22. Okay, so we're gonna go back. 19.9, 20 point. There we go. 20.02 volts, right? Let's check if that's correct. There we go. So we've got our peak-to-peak voltage as 20.02. We've got our frequency as 10 hertz, right? Now we have said that, and then it says, set that, make it real, and record the values. We've done that, right? Good. Now we proceed. You can record all those values here. You can say the nominal values, then the measured values. You use your, if you want, you can use your digital multimeter, right? This is the digital multimeter. Like what I told you, it measures frequency and whatever. You can just go all the way up to here, right? With this one, then try to measure frequency, right? Let me just try to do it quickly. So I'll just do this, right? Just put this positive on this positive node, then negative on this negative node. There we go. There we go. Okay. Let's just see if you can see that. Let's hold it there. All right. Let's see what we put is 10 kilohertz. So I'm just gonna hold positive to positive, negative to negative. Let's see. Let's see if we can measure that. There we go. There we go. 10.01 kilohertz. Can you see that? Nope. Okay. I shall redo again and hold it. There. 10.02 kilohertz, right? 10.02 kilohertz. So we just verify that, right? Whatever we're giving as input there is what's being shown there, right? We can do that. So doesn't really matter. This is just a confirmation, right? Doesn't have anything to do with actually our lab procedure here, right? Just verification of whatever we are putting is correct. So we can measure that, you know, measured value, and then the inductor, there's the nominal that we're given, right? Exactly like 0.1, then whatever we measured, right? You fill in this table, that's fine. Now, it says connect the circuit in figure 1 to the function generator and overlay both input and output voltages. So what it's saying is we need to connect this circuit, right? In figure 1, we need to connect this circuit. So what I always advise people, right? Because this is gonna get messy as we proceed into deeper lengths of this sort of unit. Circuits will become complicated. So if you try and jumble up things right now without making it as clear as it can, it will be difficult when the circuit becomes complicated. So what I always advise is try to transfer what you are seeing on paper, just move it to breadboard. So I'll hold my breadboard like this, just like paper, right? So I'll put my resistor like that, then I'll put my inductor exactly like that, then I'll give my input signal there. So what I'm saying, I can draw now, I can say, fine, I'm going to connect channel 1 here and V in here, then channel 2, I'm gonna connect it here, then my ground is gonna be here, like this, right? I'm gonna connect channel 1 and input voltage here, then connect channel 2 across the 10 millihenry, then I'll connect my ground, just like that. Let's see. Quickly, so the first thing you say, build the circuit in figure 1, right? So it has got 1 kilo ohm. So I just take 1 kilo ohm resistor, right? I put it here, like that. Then I create a node there to put the 10 millihenry inductor, right? Let me just create this node, right? I create that node, 10 millihenry inductor. I could, if I wanted, I could make this inductor jump this, but since inductor is a little bit simple, so I'll do this, right? I put my 1 kilo 10 millihenry inductor. Then what do I do now? I connect my input voltage. This is my input voltage, and I'll connect channel 1 exactly where my input voltage is. In other words, channel 1 and input voltage are going to be exactly the same node, right? That's what I'm saying. So what I do is I just use a few cables, connect this cable to this, and this cable also here, just to minimize cables as much as we can, yeah? Then put this at input, right? Put this at input. Then make this clear. Then you have this one connected across the inductor. Then ground, see, I will always advise this. Grounds of oscilloscopes, inside this oscilloscope, they are tied together. So try to put grounds, because some circuits, when they become complicated and you put grounds, you connect grounds on different sort of nodes, you cancel out one of the signals. So try to put the grounds at exactly the same node. So my ground is where this other leg of the inductor is connected, right? Where this leg of the inductor is connected, that's where my ground is. And this one is where this node is, right? Across the inductor, the positive across the inductor. Then I need to connect the ground of the first oscilloscope and the ground of the input voltage, right? I need to connect these two. Just looking for a cable. There we go. I have that one. Okay, I just put this one here. There we go. And I'll put this one here. There we go. Then this ground, it's here. Right. So now I finished connecting my circuit. What I'll do is, once you finish that and you want VL across the inductor and V in, you want both of them to display, you just auto test or auto set, auto run. That's like our run. So what we see here are two signals. The input signal is the channel number 1. The output signal is the channel number 2, right? So if we go on the experiment now, just to display, we want to see what is the phase difference between these two voltages. What we have seen, we've got many ways of calculating the phase difference, but what we know is that for us to see that there's a phase shift, right? I just want you to see this. Yeah? Looking at this diagram right now. Let's make this as big as we can. Yes. You can see that this peak of this signal and the peak of this signal, they are different, right? This peak comes maybe somewhere here, this one comes somewhere here. So it means output voltage, this output voltage is leading actually the input voltage in this case, right? So what we have to do is we have to now check the phase difference. How we check the phase difference? We use knobs called cursor. We use a knob called cursor. We choose two cursors. So there are two types of cursors on the oscilloscope. There's one what we call an amplitude cursor that actually measures the differences in the voltages in the amplitude y-axis. Then there's what we call the time cursor that measures the differences in the x-axis, which is the time axis. So we will just press cursor, right? Then we get onto the type of cursors. I'll just increase this for everyone to see. Then the type of cursors, we will choose not voltage cursors, because these are two voltage cursors, this line and this line. But what we need is the time cursors. We get two cursors in the x-axis. Now we move cursor number 1 to the maximum of the input voltage. So we move cursor number 1 to the maximum of the input voltage, right? Maximum of the input voltage, right? Then we move cursor number 2, maximum of the output voltage. There we go. Right, there we go. Now we have this. Yeah, we've got now this difference. Now what we have is a difference between these two in the second division, which is that 28 microseconds. Yeah, you can see that 28 microseconds. Now that 28 microseconds, we call it delta T. Delta T, right? We call it delta T. Right? But then now we need to see what's the relationship between delta T, and the phase difference, right? So what we know is that this delta T, this axis, this delta change in time is actually changing the period of this signal, right? So this is actually divided by T. If we divide delta T by T, what we find there is just a ratio, right? A unitless number, which is a ratio of the change in the period, just time-wise in the period, right? So if you want to see what was the phase difference in maybe degrees or radians, we have to multiply by the one complete cycle, which is either 2 pi or 360 degrees. So multiply this by 360 degrees. In this way, you will find what is our phase difference. So in this case, if you just go on with this calculation, our delta t became 28 microseconds. 28 microseconds divided by our period, right? Look at it. We're given that we should put a frequency of 10 kilohertz. Our period, relationship between period and frequency, F is 1 over T. So our period actually divided by 1 over 10 kilohertz times 360. If you do this mathematically, you will find what is the phase difference in this case, right? So you find the phase difference in this case. That goes on our question number 3. Now, on question number 4, it says, now create an RLC circuit, exactly as figure 2. So what it was just changing is we are changing the position. Well, not changing the position. We are removing the 1K resistor and we put a 100 ohm resistor. Then we actually move, we include a 0.1 microfarad capacitor. So we just, again, as the display looks, I'm just going to connect exactly like this. Okay, now be with me, let's go. We remove this resistor, so it's up to us to just disconnect the input voltage at this instant, right? Input voltage at this instant. Then I'll remove this 1K resistor. I'm gonna put a 0.1 microfarad at that point where the resistor was. There we go, right? Then I'm gonna put a 100 ohm resistor. At the other end, which was initially the ground, right? But now my ground is no longer at that node, right? Take this node. My ground is no longer here, right? I'm gonna change that ground because there's going to be a resistor connected across before you actually go to the ground. So be in mind with me that our ground has changed indefinitely. From now onwards, our ground is no longer my ground is no longer here. All right, my ground terminal is now here. They're at the end of the resistor. Let's take that note, right? My ground is no longer at this point, it's now at this point, right? So I'll change my ground to that point. Now I need to give the input voltage. So my input voltage will come to the 0.1 microfarad capacitor and to the ground, which is the other side of the resistor. So I will get my input voltage from for this, the other side of the resistor, then 0.1 micro ohm, where my input will come in, right? Now, as I said, my ground is changed, so the ground terminal becomes this node. Right. Now. So they're saying create this RLC circuit, ensure to connect the resistor, right? Function at this point, the reference voltage for the oscilloscope channels, right? Check that you can view input voltage and voltage across the resistor on the oscilloscope. Okay, I'll display the voltage across the resistor soon, but right now I just want you to see the voltage across the inductor, not the resistor, right? The inductor. So I'm just gonna auto set. What do you see right now is the phase shift voltage across the inductor. Okay, this is the voltage across the inductor, but then they are saying voltage across the resistor, right? So I'm gonna measure the voltage across the resistor. So this is voltage at the other end of the inductor and ground, in other words, right? So I'm just gonna change that. Was channel 2. This is my channel 2. It was connected this side of the inductor, right? Then now it should be connected at the other end of the inductor. There we go. Then we put an inductor there, right? Then I just auto set. Right? Now I view again 2 signals. If you actually view these signals closer, then I can actually just try to bring this one closer to here so you guys can see the phase shift, right? What I can just tell you from now onwards is that because of that resistor, the phase shift should have been decreased a little bit. because we are saying whenever you put a resistor, you decrease the phase shift, right? You decrease the phase shift. You try to make the circuit resistive. A resistive circuit is a phase shift of 0, right? Then whether you put an inductor or a capacitor, then the phase shift ranges from minus 90 to 90, right? That's more theory. And then it's saying examine the way that the magnitude of the resistor voltage changes as the frequency is swept from 1 kilohertz to 10 kilohertz, and draw this graph by hand. So in other words, they are saying, try to move this frequency, right? Try to move this frequency. So I'll just make this one a little bit bigger. Okay, oh, this one bigger. Okay, let me move it upwards. So in each and every section of this, what you'll be doing, let's move this position like that. Let's move this one to the 0 position, and you move this one to the 0 position. We'll try to make everything in the, there we go. Right, I'm having input signal and output signal at that point, right? Now, what we want to do is we want to change the frequency from 1 kilohertz to 10 kilohertz, right? I just want you to see what will be happening. So I'll start from the minimum, 72 hertz. Let me start from 1, go down, yes. I'll start from 1 kilohertz, 875 hertz, fine. Auto set that, right? Now I want you to observe what will be happening. I'll again just move this to the center, and I'll move this to the center. Now. Phase shift, that's what we want to see. The difference in the phase shift is I increase this, right? From 872, I'm gonna increase and increase the frequency, and increase the frequency, and increase the frequency, and increase the frequency, increase the frequency. As I increase, I just auto set at one point. Then I'll take them together again so you can see what's happening. Again, I'll increase the frequency, 4, 5, 6, 7, 9, back to 10. I'll just auto set that. Right? Now, what you're supposed to do at that point is just to measure the relationship now between the phase shift, which is where you use those two cursors. You just take amplitude, time cursors, use two time cursors, use this formula that I applied here, then plot a graph. That's it. Okay? Now, last section of this experiment is saying examine how the phase changes around the frequency F0 you have located in the previous task. What is the phase of the following frequencies record results? Yeah. Now, at that point, okay, what I'll just mention here is that once you draw this graph by hand, right, of this magnitude of frequency, right, what is the frequency F0, right, at which the resistor voltage is maximum? Now record the value below. So once you have this frequency F0, at which you find the resistor voltage, which is the voltage across the resistor, you find it to be maximum. So you find maximum peak to peak of channel 2 at that point. Then you determine at that frequency, because once you draw a graph, you see at the frequency that it becomes maximum. Then because you're going to plot frequency versus resistor, so what you will have will be a curve. So at that curve, you see a turning point where it becomes maximum. You record that relative frequency to F0. Then using that F0, you complete the last section of our lab, right? And that concludes this lab session. I hope you guys actually learned something from equipment to how we measure using the digital multimeter, and what this oscilloscope is used for, and how we operate our function generator. This one, I didn't use it. I mean, it's a DC power supply. Should have used it in UNG 125 or 225, but still, Nevertheless, I mean, maybe when I use it, then I'll show you again. All right, good luck and take care.